Good morning to all. This is M. Visalakshi, Assistant Professor, Department of EEE in Tandai Periyar Government Institute of Technology, Vellore. Welcome to e-learning class. And today's topic from Power Electronics, multiple pulse width modulation. So before moving to pulse width modulation, multiple pulse width modulation, we will see the introductions of pulse width techniques. So generally, fixed DC voltage will be given to the inverter and controlled by AC voltage, which is obtained by adjusting on and off period. And this is controlled output voltage is pulse width control. So this by controlling the output voltage is PWM technique or control. And the main technique of using this will be to reduce the overall harmonic distortions in load current, and varying input DC output voltage can also change, and the amplitude and harmonic content of the waveform can controlled by the duty cycle of the given switches. And some of the advantages of PWM is obtaining without any additional components, and lower order harmonics can be eliminated or minimized with output voltage control, and higher order harmonics can be designed or filtered easily. And also some disadvantages is there in PWM technique. One is SCR will be silicon control rectifier are very expensive and which possess low turn off times. So these are the advantages and disadvantages of PWM technique. And some of the types are single pulse width modulation, multiple pulse width modulation, sinusoidal pulse width modulation, modified sinusoidal pulse width modulation, and the last one is phase displacement control. So from this we are going to see multiple pulse width modulation. So this is the block diagram for MPWM, multiple pulse width modulation. And here main characteristic here is by a constant amplitude, also to obtain the inverter output control and reducing the harmonic content. Width of the pulse will be same. So by varying this, the sine wave can be evaluated at the center of the same pulse. So many pulse will be given in each half cycle of the output voltage. So this is the block diagram, and also it's an extension of single pulse width modulation. Okay, and also it is an equidistance pulse or half cycle can be used. So from the figure given, it can be generated by comparing with the square wave voltage waveform. Okay, square wave with the VR voltage of a frequency omega with triangular wave. Okay, with a triangular carrier wave of carrier wave with the replacement is Vc of a frequency omega c. Okay, and by triggering here, so from the diagram given, so this is my carrier signal and this is my reference signals. Okay, so this is your carrier and this is your reference signal with a different angle representations. Okay, here the carrier signal is a triangular waveform and reference signal is a DC voltage. By triggering the pulses for thyristors generated at a point of intersection of carrier and reference signal wave. So how it is represented as F suffix C and frequency, or represented in hertz for carrier signal and reference signal. Okay, and this can be calculated by 1 by fc. So 1 by carrier frequency will be pi by 4, and suppose when it is 1 by 2 times of frequency, the value will be pi. So and so on, it will be increased. Okay, so from this we can find the number of triggering pulses. So this is the pulse obtained waveform. So here, as I told already, width of the pulse can be varied by changing the amplitude of the DC reference signal. Okay, and here this output frequency can be determined by the frequency of the reference signal, and output voltage can be controlled by the modulation index M. Okay, so here carrier frequency of a triangular wave and F naught be the output frequency. So here number of triggering pulse will be 4 by pi into pi by 1. Okay, so in previous slide we saw that carrier frequency as pi by 4. Okay, and 1 by 2 f frequency is pi. So that is the value here obtained. So after cancelling, we'll be obtaining the value as 4. So number of triggering pulse is 4. And for triangle wave will be 1 by fc. Okay, so 1 by fc. For square, the width of the half cycle will be 1 by 2f. So this is what your width for triangle pulse. Okay, so this is the, as I told in previous slide, so number of pulse generated per cycle can be determined. So for triangle 1 by fc, for square wave half the cycle will be 1 by 2f. So from this we can find the number of pulse per half cycle. So formula will be length of the half cycle of square reference wave to the width of the triangle carrier wave. So that is 1 by 2f. Length of the square wave is 1 by 2f, and triangle wave will be 1 by fc. So when I am just calculating fc by 2f in terms of omega c by 2 omega. Okay, so here this can be controlled by the range 0. Okay, so here range will be 0 less than VR less than VC, and similarly width will be 2D by N, and this can be varied by 0 less than 2D by N less than pi by N. Okay, so these are the ranges. By adjusting the magnitude of VR of a reference square wave, so pulse width will be 2D by N. Okay, so this is the formula to calculate the output RMS value. So V naught RMS will be equal to 1 by T of 0 to T V square omega T d omega T half. So period will be 2 pi for a 2 pulse of equal width. For first pulse, it is located at pi by p, and width will be pi by p minus del by 2 to pi by p plus. So we can write pi by p plus or minus del by 2 for width. And for first pulse and value of complete waveform will be 1 by 2 pi. So this is your width. Okay, pi by p minus del by 2 to plus pi del by 2 Vs square d omega t whole half. So after calculating, differentiating and integrating, Vs square root of del by pi, okay, into del by pi. And some of the advantages are there. So distortion factor is reduced comparing with the single pulse modulation. Why? Because as I told in first slide, it is similar to single pulse modulation. Only some changes will be appeared for multiple pulse width modulation. So distortion function in the sense effective value of harmonic component to the fundamental components, and the value of P increases the amplitude of lower harmonic reduces, and there is a disadvantages. So increased number of pulses, switching losses are increased, and also the control scheme will be complexity. Thank you.